Hey team, today we're going to begin our conversation about inverse functions. We'll do most of our notes so that tomorrow we can be set up to do a lot of practice. And practice is really what's going to help us understand inverse functions because they can be a little bit tricky at first. And so I do want to start with this statement at the top of our notes that says in math, an inverse function undoes the work of another function to get us back to where we started. And so looking at this first example, we have some function f of x, and f of x is equal to x plus 3. What would the inverse operation be of adding 3? Whenever we learn algebra, we actually talk about inverse operations. That is what we call them when we were trying to isolate x or solve for y or whatever it may be. If I wanted to undo adding 3, I would subtract 3. And let's think about it in terms of an example so that it can really click for us. Let's say originally right now you have $0, that's sad. I feel like I have $0 right now. And if I give you $3, how would I undo that? Well, I'd undo giving you $3 by taking those $3 away from you, by subtracting those $3 from your bank account. That is the inverse operation for this first example. If we were originally adding 3, if we subtract 3, that gets us back to where we started with just x. Let's take a look at another example. This second example, where f of x is now 2 times x. How would I undo this multiplication of 2? What would my inverse operation be? We would need to divide by 2 because division is the inverse operation of multiplication. If I, originally start out with, 2 pennies, I multiply that by 4 to get 8 pennies. How do I get back to 2? Well, I divide by 4 instead of to undo that multiplication of 4. And so in this case, division is going to be our inverse operation. We're going to do one more example before we move on to the rest of our notes. This time, our function is equal to x squared. This one's a little bit tougher. What would our inverse operation be to undo squaring our x? Yeah, this one's a little bit tougher. But what we know about exponent properties, what we know about trying to undo something that's being squared, if something is being squared, then we will square root it. In the same way, if we had x cubed, how do we undo x cubed? We will cube root it. So that's nice. Whatever our power is, if we take that root, those things will cancel out. We will just be left with x. That is the inverse operation. All right, and so let's go ahead and actually apply some numbers to these examples. If we're looking back at example 1, let's say I want to start out with 7 donuts and I add 3. So I am inputting 7 into my function for f of x. That's going to give me 7 plus 3. That will equal 10 donuts. And so if I'm thinking about my input and my output, and I want to write a point that I can plot on my graph, remember we're always doing x comma y, you tell me what is the x value that I plugged into this function, and then what is my y value? What was my output? I plugged in 7 for x, so that is my x value. And when I did that into f of x, my output was 10. That is my y value. And earlier we said the inverse operation of adding is subtracting. So I'm going to write a new function. I'm just going to call it g of x. I'm going to say, hey, in order to get back to where we started, we're going to have some number and we're going to subtract 3 from it. In this case, if we are using the same numbers that we did for f of 7 equals 10, in order to get back to 7 from 10, I am plugging 10 into this function. G of 10 is equal to 10 minus 3, and that gets me back to 7. Again, if I'm trying to think about a point that is represented by this work I have here for g of x, or g of 10, my x value is 10, because that's what I plugged into my function. That is my input. And my output, after I did my evaluating, was 7. Now I want us to look at something. I am telling you that g of x, this function, we just said it is the inverse of f of x. What do you notice about a point that is on an original function compared to a point that is on our inverse? That's right, my x's and my y's flipped, right? For my original function, f of x, 7 was an x value that I was plugging in as an input. In my inverse, that 7 is now an output. It is a y value. Same thing if I'm looking at my 10, which was an output or my y value for my original function, f of x. It now becomes an input or an x value on my inverse function. And that is going to be our first key point when it comes to inverse functions. If the point x comma y is on f of x, then the point y comma x, again because our x and y's are just flip-flopped, is going to be on its inverse. Our x's and y's are switched. And while we think about that, I want to give us one more example. So what this key point is telling us is that, let's say f of x and g of x are inverses of each other. So are inverses. Dot, dot, dot. If the point 2 comma negative 5 is on f of x, then that means that the point negative 5 comma 2 is on g of x. That is exactly the kind of conclusion that we can make based on this first key point. And that is going to be a really handy piece of information for us as we move forward. And so generally, right, these first couple examples, super straightforward, right? Inverse operation of addition, subtraction, inverse operation of multiplication is division, etc., etc. And that's cool, but what happens when we get to a more complicated function like we see here, where f of x is equal to the cubed root of x plus 1, all divided by 7? Like, what? This is going to be such a key process for us trying to find the inverse of f of x. And so it's really important that we are following along with these steps. I'm going to be going at a pretty slow pace to make sure we are understanding. We'll do lots of CFUs along the way. And so if we're trying to find the inverse of f of x, our first step is to replace f of x with y. Replace f of x with y. Done that here. Everything stays the same. I just have a y equals instead of f of x equals. The reason we do that is because step 2 is going to be to essentially enact our first key point. To apply it to this situation, we are going to switch or flip-flop our x's and y's. And so when I do that, I'm going to have x equals the cubed root of y plus 1 divided by 7. And when we do that, that sets us up for our third step, which is to solve for y. When we solve for y, that equation that we get is going to be our inverse of f of x. And so when we do that, this is why we went over some of those more simple examples with some of our inverse operations as review, because those are going to come into play right now when we are trying to solve for y, which is step 3 of this process. If I'm looking at what I have here, first I need to multiply both sides by 7. So that my 7 in my denominator on the right side of my equation cancels out, and I'm left with 7x equals the cubed root of y plus 1. And honestly, like, understanding that we needed to do that first kind of makes sense based on what we know about solving radical equations, which we have done earlier this year. Our first goal is to isolate this radical, and we have done that. We've gotten rid of that dividing by 7. Now, just like we talked about earlier, in order to get rid of a cubed root or cancel it out, we're going to take both sides to the third power. We're going to cube both sides. When I do that, I'm going to have 7x, all of that cubed, and that's equal to just our argument, whatever's underneath our cubed root, which is just y plus 1. The last thing we need to do, I'm going to have you tell me, because I know you know what to do. What is the last thing I need to do to isolate y? Heck yeah, we got to subtract 1 from both sides. And so when we do that, we get y equals 7x cubed minus 1. That gets us to our last step, which is just notation. We're going to replace y with f inverse of x, because we started with f of x, and so we're finding f inverse of x, which we represent with this like little negative 1 after our f. And when we do that, we get f inverse of x is equal to 7x cubed minus 1. That is our inverse function for f. Fantastic. Let's go ahead and stamp this last point with our notation just one more time. If f of x has an inverse, we write its inverse as f inverse, so f to the negative 1 of x.